problems, but these can be extremely tough.
Yeah, it's just like hard for me to figure out. Like, I know what the definition of a permutation and combination is.
Okay.
It's just hard for me to figure out which one is which when I'm doing them.
When to use them. Use combinations when order doesn't matter. Use permutations when order counts.
Okay.
Okay? In other words, if I said, what's the odds of being dealt a heart flush with 5 cards? Order doesn't matter, because it doesn't matter if I got, in other words, all I care is that all 5 cards are hearts. Doesn't matter if my first one's an ace and the second one's a deuce and the third one's a king, or my first one's a king, the second one's an ace, the third one's a deuce. It's the same 5-card hand regardless.
Okay.
So that's a combination problem.
Okay.
If I say, what are the odds of getting the ace of hearts with my first card and the king of hearts with my second card, that's a permutation situation. Order matters.
Okay.
Okay? So why don't you give me the word problem and we'll see if we can figure, or whatever problems you have, go ahead and give them to me and let's tackle them.
Okay, well, this one says, how many ways can the uniforms numbers 2 to 24 be assigned to the JV baseball team if there are 14 players on the team?
So this is either 24, the total number is 2 through 24. There's 24 options, 24 numbers there that we can assign. Well, there's only 23, aren't there?
Yeah.
Excuse me. You subtract the 2 and add 1. And there's 14 players. So we're going to take 23. Think about this maybe in a different way that might be helpful.
Okay.
There's the 14 players. How many numbers can this guy get?
He can get 23 numbers.
23 choices.
Once. Yeah.
How many choices does this guy get? Once that guy's gotten his number. Okay. And so forth and so on.
Oh, I see. That makes it make more sense.
Well, it's easier to think about. Now, is this a permutation or a combination problem? Well, let's figure it out. We certainly know that that's 23 times 22 times all the way down to 10. So if it was a combination problem, it would be 23 choose 14, which is going to be 23 factorial over 14 factorial times 9 factorial. If it was a permutation problem, it would be 23 factorial over just 9 factorial. Does that equal this?
Yeah.
It does. It's a permutation problem. Now, that's kind of a lousy way to figure it out, but it verifies for me that it's a permutation problem. And
wait, why did you do the 9?
Because NPR is n factorial over n minus r factorial.
Oh, okay.
And this becomes 23 factorial over 9 factorial, which becomes 23 times 22 all the way down to 10.
Okay, I see.
Okay?
Yeah.
Now, let's see if we could have figured out that it's a permutation problem instead of a combination problem without doing this whole thing over here. Order matters. Because this player has to get a number, and not sure I can explain that. I know it's a permutation problem because of the way it works out. In other words, this is easy to explain, like you said, you understand. Once the first player has gotten a number, there's only 22 left for the next guy. And I can tell that that's 23 factorial over 9 factorial, which fits that definition. So it's a permutation problem. Let's go to the next one, and maybe we can figure out a better way to figure out whether order matters or not.
Okay. So this question says, how many ways can a committee of 8 be chosen from a class of 18 sophomores and 14 juniors under the following conditions? And then the first question is, all students are equally eligible.
Okay. In this committee, does order matter or not? This is an easy one to see.
No.
No. If I have a committee of 3 people, I don't care if it's A, B, C, or C, B, A. It's the same committee. So order does not matter. So it's a combination problem. So it's total of 32. We're choosing 8 out of those 32. Now, this is going to be 32 factorial over, and the way I remember this one, there's 2 r's and 2 n's. I know that there's an n minus r factorial there. Question is, what is this? Well, if there's 2 n's and 2 r's, it's got to be r factorial. That's how I remember it. Because for a long time, I could never remember whether this was n or is that r.
Okay.
So this becomes 32 factorial over 24 factorial times 8 factorial.
Okay.
Now, the second part of these that is going to give me trouble, maybe. What's the next part?
Okay. It is
The second condition.
the committee must include the same number of sophomores as juniors.
Well, I'm tempted to say that that means that we're choosing from 14 sophomores and 14 juniors.
Yeah.
So maybe this?
I can check the answer.
Obviously it's less, right? In other words, we had more options when we can include everybody.
Yeah.
Now, we're not going to be able to include everybody. We're not going to be able to draw out of all 18 sophomores. We're only going to be able to draw out of 14 of them. So, let's see what this number is. That's 28 factorial over 20 factorial times 8 factorial, which is 28 times 27 down to 20. Divided by 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Why don't you stick this in your calculator? You know how to do that?
Okay. Yeah.
In other words, I don't want to do all this arithmetic over here.
Yeah. It would be 3,108,105.
See if that's your answer.
The answer is for B, 3,000,000.
That'd be right.
63,060.
Really? It's not right.
Yeah.
Ah, I see what's going on. I know what I have to do. If it requires 4 of each, then it's 18 choosing 4 plus 14 choosing 4. Come up with this number and this number, add them together, I bet you get that 3 million.
So would it be multiplication or addition?
Well, in other words, we know this committee, we're going to have to choose 4 sophomores out of 18 without regard to order. So it's 18 choose 4. What's that number? 1,000,000 what?
It's 18 choose 4 is 3,060.
What's 14 choose 4?
1,001.
Multiply those two together and you're going to have your 3 million answer.
Okay.
Question is, why do we multiply them? Seems to me, because for every one of those choices, we have this many choices for the other.
Oh.
That's why we multiply them. In other words, there's 3,060 ways to pull your 4 sophomores out. And for every single one of those 3,060 ways, we have 1,001 ways to pull 4 juniors out. So it's clearly multiplication.
Okay.
Multiply those two numbers, you have your answer.
Okay.
So the answer, you could say, would be 18 choose 4 times 14 choose 4. And logically, it makes complete sense to do it that way.
Okay.
Okay. Have an answer sometimes is a godsend. You can figure out how to do the problem. Thank you. That's why calculus, they try to give you answers for every problem you get, not just the odd ones. Because a lot of calculus problems are so hard that sometimes you end up having to look at the answer to figure out how to do the problem. I mean, that's a fact of life with calculus. But if you had to study it without answers, it'd be a lot harder. Let me put it that way.
I bet.
Okay, what else you got?
Okay. So this one is a question about normal distribution, something like that. Okay, it says life expectancy for a baby born in 1990 is normally distributed. The mean is 75.6 years and the standard deviation is 4.
What's the mean? 75?
0.6. Yeah, 75.6.
Okay. You're going to say, what are the odds of somebody living to be 79?
Oh, yeah. it says determine the probability of a baby born in 1990 living for longer than 79.6 years.
Okay. Well, we know the area under this normal distribution curve. We know that 68% are within one standard deviation. So if I go out to 79.6 years to the right and 71.6 years to the left, that's one standard deviation. Okay? And I know that 68% of the curve lies under one standard deviation. So if I want the odds of living, what was the question? Probability of living greater than?
For longer than 79.6 years.
Which is this area all over here.
Oh, I think I know what I did wrong.
Okay, hold on. I didn't mean to erase my whole thing. But what's this percentage over here? And this?
Is that 13.5?
No, it's, in other words, the rest of the curve is 32%, right? Equally split. So we got 16% over here, 16% over there. That's your answer. In other words, we're looking for the probability of falling in this area right there. Not this over here, but it's symmetrical about the y-axis. So we can certainly figure out that this area is 16%, half of 32.
Okay.
Okay.
The next one says, determine the probability of a baby or a boy born in 1990 living between 71.6 years and 87.6 years.
Okay. 87.6 is going to be 3 standard deviations, right?
Yep.
So 87.6 is exactly 3 standard deviations. And we know that 99.7% lies within 3 standard deviations.
Okay.
So you said between 71.6?
Yeah.
Okay. Well, we know that it's at least 68%, right? This area, 8%.
Yep.
And we know that, is it 99.7? Is that the third key number, or is it 99.8? Do you know?
I think it's 99.7.
Yeah, I think so too. So 99.7 would fall between this point and the equivalent point on the low side. But,
okay.
So let's see, let's analyze this. If 68% falls there, 34% falls there. Okay, this part. And if 99.7% falls between my 2 vertical lines, then 49.85% falls right there.
Okay.
Add
So then
34
add it.
to that, and you've got your answer.
83.85%. Okay. All right, the next one is how many 7-card hands can be dealt having exactly 3 spades, 3 clubs, and 1 red card?
These are the ones I hate.
Yeah, me too.
Well, there's 52 cards. We're going to choose 3 spades, and we don't care what order they're in. So the way to get 3 spades in 7 cards would be 7, choose the 52. No. These are so hard. I got to just, it requires such different kind of thinking. Think for just a second. Well, red cards, there's 26 red cards out of 52.
Yep.
So there would be 26 ways to choose a red card times 7. Because sometimes it's helpful, for me at least, to lay out our 7 cards. And the red card can go in any of these slots. Now, there's 26 ways to put it there. There's 26 ways to put it in each slot. So there would be 7 times 26 ways to get the red card in there.
Okay.
Three spades. How many ways can you choose 3 spades? Well, we're choosing from 52 cards. There's 13 spades. So every one of these slots has this many ways to put a spade in it. But it doesn't have to be these first 3. It could be the next 3, or the next 3, or the next 3. So 7 choose 3 is 7 factorial over 4 factorial times 3 factorial, which is 7 times 6 times 5 over 3 times 2. So that is 35 over 2, or 70 over 2, 35. So there's 35 ways to choose to put a spade on our 7 cards. And there's this many ways to choose a spade. The only way I'm going to be able to answer this is to go in my textbook and find a similar problem and see how they do it. This is about the level that starts making me do that. In other words, go ahead.
In the key it said it uses 13 choose 3 times 13 choose 3 times 26 choose 1.
Ah. Yeah, I see now. In other words, there's that many ways to choose 3 spades out of the deck.
Oh, okay.
There's this many ways to choose 3 clubs out of the deck, and there's this many ways to choose 1 red card out of 26.
Okay.
And for every single way that you can choose 3 spades out of 13, each of these you're going to multiply because you can do each of those also. For the same reason we multiplied in the last problem.
Okay.
Because for every one of the 3,000 ways, there was 1,001 ways for the other. So we multiply. Well, for every one of those ways, there's this many ways also. So we're going to multiply. I understand the answer. I may not be able to explain it exactly, but that's pretty close.
Yeah, that makes more sense to me.
I mean, here's another case where having the answer really does explain to me what's going on. In other words, your first step is to choose 3 spades out of 13 cards, and 3 clubs out of 13 clubs, and 1 red card out of 26 cards. Once you've chosen those, for every way that you had for choosing 3 spades out of 13 cards, you've got, boy, I'm having a hard time putting it into words. Hopefully you understand what I'm trying to say.
Yeah, I understand.
Almost easier to go back to the other problem and figure out why we multiplied. Because there were 3,060 ways of getting 4 sophomores out of 18 sophomores. And for every single one of those ways, there was 1,001 ways of getting 4 juniors out of the 14 juniors. And so it's clear that we're going to have a lot of combinations. For every single one of those, we've got 1,001. That means we multiply these 2 things together. Well, this problem is actually no different than the one we just looked at. I should have looked at this problem as my example. The one we're looking at is we have 7 cards, and we have 3 spades, but actually we have 13 spades that we need to choose 3 out of. We have 13 clubs that we need to choose 3 out of, and we have 26 red that we need to choose 1 out of. So we're still going to multiply those possibilities for the same reason we multiplied these.
Okay. That makes sense.
Yeah, it actually does. I can't believe I didn't see it. In other words, this problem is the same as this problem. It really is. Exactly the same. It's just got 3 levels in it instead of 2. Or 3 groups instead of 2. Here we had sophomores and juniors, whereas in the other one we got spades, clubs, and red cards.
Okay. Yeah, that makes sense.
Okay.
Yeah.
You were just looking for a half hour tonight, right?
Yep.
Okay, you good to go?
Yeah, I think so.
Okay, I hope I've been helpful. This is a hard subject.
Yes, definitely.
Hard subject matter.
Yeah.
It'll be easier when you get into limits, calculus.
Yeah.
I've just always found it extremely tough. And I've dealt with probability my whole life. I've played cards my whole life, and I'm pretty good at probability, but boy, these combination and permutation stuff, definitely difficult.
Uh-huh.
Okay, Ellen. I'll let you know.
Well, thank you so much.
You're welcome. I'll talk to you next time.
Bye.